So our ultimate goal is to construct what are called probability models for our probability experiments. We would like to have a complete description of all of the outcomes and all of the probabilities associated with those outcomes. And now that we've learned about the probability basics, we can start this process. So as an example, we are going to start with a very simple experiment where we flip a coin twice. And we've talked about tools like tree diagrams to help us determine all of the possible outcomes. So the sample space of this experiment consists of 4 different outcomes. You could get heads on both, heads first, then tails, tails then heads, tails then tails. If we wanted to think of this as a partition, we would use proper notation and we would partition this set into these disjoint events. Remember that all of these things are exclusive. They cannot happen together. Now, we also learned about how to assign probabilities. And here we can use the classical definition to assign probabilities to this particular experiment. So for instance, you have a 1/2 chance to get a heads on the first flip because there are only 2 outcomes on flip 1, heads or tails, and you have equally likely shot of getting them. We also discussed independent events, experiments that have no memory of what happened in the previous stage. And so this qualifies as an example of independent events. So this picture and this description tells us everything we need to know about this experiment. But in order to make progress down the line, we need to introduce some mathematical tools that will help simplify things later. The first is the fundamental concept here. This is something called a random variable. Now, a random variable isn't really a variable in some sense. It's really a function that takes something from the sample space and turns it into a number. So it's essentially a function that assigns a numerical value to every outcome in the sample space. So the first step is to know what's in the sample space. So in terms of a picture, you need to know every particular outcome that's in the sample space. And once you have it, you can assign to it some number. Now, the notation that we are going to use throughout this entire semester for random variables are capital letters. And so in this particular case, the function here that we're going to talk about is a capital X. So I'm putting bars on the top and the bottom. And this random variable will take one of our outcomes from the sample space and it will turn it into a number. Now, that random variable could be anything. You could assign any number you want. So at the onset of your problem, it's really important to define what the random variable is measuring. So in the example that I just did with the 2 coin flips, we are going to define the random variable as talking about the number of heads that we get in our experiment. And so what the random variable will do is it will take an outcome. So this is one of the outcomes from our experiment, 2 tails. And what it will do is then assign a number to it. Well, naturally, if X is supposed to measure the number of heads, then this outcome should get a 0 as its value. Similarly, if I take the outcome TH, this should get a 1. The outcome HT should also get a 1, whereas the outcome HH should get a 2. We could have what are called discrete random variables versus continuous random variables. Discrete values are things that are listable. So you can write them 0, 1, 2, 3, or any sort of list, and it's usually finite, but not necessarily. Continuous variables or continuous values are not listable. So for instance, the real numbers are not listable, because if I ask you what the question, what's the next number after 0? There are infinitely many choices. You can't possibly list the next one. Continuous random variables, there are typically infinitely many of them. In the first part of the course, so for the next little while, we are going to study this first. We're only going to study discrete random variables first. So everything that you read about in your textbook to do with continuous variables, we're just going to put on the back burner for now. We are only going to talk about discrete random variables for now, for the next couple of weeks. So in the context of discrete random variables, the next important idea is something called a probability mass function, which I'm going to abbreviate as a PMF. So a probability mass function is essentially a piece of information that tells you everything about all of the outcomes and their probabilities. The easiest thing for me to say is it's a table showing all the values of your random variable x along with a probability for each x value. Now, in the context of our 2 coin flip problem, let's again state that x is the number of heads that you get. The probability mass function is just going to be a table. One of the entries in the table is going to list all of the possible values of our random variable. And in this case, there are only 3 of them, 0, 1, or 2. The next row in the table is going to list the probabilities for each one of those outcomes. And this is the part where all the material from chapter 1 kicks in. We have to remember how to calculate or determine all of these things. Now, if we go back to the table above, so if I just scroll back, so for instance, this outcome is going to have a probability of 1/4 because they're 2-stage experiments and you multiply them together. And it will turn out that each one of these has a probability of 1/4. However, some of the outcomes occur only once, whereas the other outcome occurs more than once. So note, the event x equals 1 means you get 1 head flip. And it means that there are 2 outcomes. You could have heads, tails, and you could have tails, heads, and these are disjoint. So the probability, or the event x equals 1, is made up of the union heads, tails with tails, heads. So the probability of getting x equals 1 then becomes the sum of these 2 individual probabilities. Now there's another note with mass functions. Because the sample space is usually partitioned into all of the outcomes, it has to be partitioned up into all of the outcomes in that your random variable can take. This goes on all the way down to the end. If you were to apply the probability function to each of these, you would, again, all of these are disjoint. And what you'd come up with is that this has to come up with a really important result. You would get that the sum of all of these individual probabilities, where I goes from 1 to n, they all have to add up to 1. So the bottom row of this table, all these probabilities need to sum up to 1. A better way of putting it is that we could also use a bar chart to visualize the mass function. So a bar chart is a very simple and easy way to see what's going on in our experiment. In this particular case, there are only 3 outcomes. On the horizontal axis, we will list all of those outcomes, and on the vertical axis, we will just draw a bar, a height, to represent the probability. So in this particular case, it's very straightforward to visualize what's happening in our situation.